So let's summarize. We started by having high-dimensional correlated data with a strong suspicion that the dimensions were really redundant in some way. So remember that example, you had height and refu, where refu in Swahili means height. So they're really the same variable, you're just getting some noise in the observations. And what you would like to do is you would like to reduce the dimensionality of that, uncover that factor that captures both height and refu. So the way we do that is first we center the points. It's an important step, don't forget it. Right? So we take the origin and move it to be right in the middle of the data points so that every mean is exactly 0. And then we want to find a dimension along which the data is as spread out as possible. So the red is a bad dimension because the data is not spread out and faraway points will end up being close together. The green dimension is good, we want green. The way we find the green dimension is we take our data, we find a covariance matrix, so that's how height and the refu move together. And then from the covariance matrix we find the eigenvalues and the eigenvectors. Remember the eigenvectors, vectors such that when you multiply them by the covariance matrix they get longer or shorter but they don't turn. And then the eigenvalues are how much longer and how much shorter they become. And they also have this cool property that they tell you exactly how much variance you're getting along that eigenvector. So it's a complete, I guess in 2 dimensions you can do it by hand. In 10 dimensions you cannot do it by hand. So how do you implement it? Well, if you work in a godly language, in a high-level language, it could be as short as that. So that's how you compute eigenvectors in MATLAB. Right? Very complicated. Right? And you get eigenvalues and eigenvectors in one go. Right? So in a high-level language, it's trivial. Okay. So once you've identified your eigenvectors and eigenvalues, you're going to look for m eigenvectors, and you're going to pick the ones that have the highest eigenvalues, because they are the ones that span most of the variance in your system. And then once you've identified them, so in this case, I'm in 2-dimensional space, so I'm going to look for 1, and the one that has the highest eigenvalue is this green vector E. So that's the dimension that I want. So then what I'm going to do is I'm going to project all the data to that dimension. Right? And the way you do the projection is you take the dimension vector that you identified and you do a dot product between it and every single instance of the data. Right? So what you end up with, this E becomes your new coordinate, and I'm drawing it horizontally because that's my X now. Right? I only have one dimension, so that's going to be my one dimension. The old dimensions, height and refu, are shown in gray there. So what we've done is we've basically, another way to think about what PCA does, it rotates the space in a way that makes it a little bit more sensible and decorrelated. So we've rotated the space, the old dimensions are still there, and we're projecting all the data points to this new dimension. So you end up with low-dimensional data that is also uncorrelated in the new dimensions. So it makes no sense to say what's correlated in 1D, but if you were projecting to 2D, you would end up with data that is as uncorrelated as possible.